Welcome to Four Questions with an Engineer, a podcast about bearings and motion control. Each episode discusses one aspect of motion control and the bearings that make it happen. We are joined by Corey Helgeson, a mechanical engineer from CCTY Bearings U.S. office. On today's episode, we're talking about finite element analysis. Corey, can you tell us what is FEA?
FEA stands for finite element analysis. It can also be called FEM for finite element method, or some people will just say simulation. So a part is modeled and broken down into finite elements. That's where the name comes from, through meshing. And then the solver will use differential equations to solve for each element, and that will provide a solution for each element to give a solution for the overall study. Basically, you're simulating how a part would react in a given set of conditions, whether it be a load, a prescribed displacement. There's really endless types of studies that can be done, and there's a lot of theory, and it gets very deep. So overall, it's just simulating how a part is going to react to a certain condition.
Understood. Talk to us about the benefits of finite element analysis.
So some benefits of using FEA are cost, time, and optimization. For the cost, you save cost in both making tooling, molds, and also just producing parts. A good example would be the boot or the seal mold and the seal. It's an expensive mold and it takes cost and time to modify as well. So if you can do some FEA to get the seal in a better place before you produce the part, you're going to be making less molds and you're going to be making less parts. At the same time, for something like a seal, usually it's not going to fail because if stress is too high in a couple tests. That's something that happens later in the life of the part. So it's not something very obvious just from making a part. It's good to look at FEA and see where the high stresses may be. Another benefit is time. Obviously, it takes time to produce parts, to produce molds, then to test them. This all takes time. Can be reduced drastically if you use some FEA to get to a better place with the overall part before you start making it and testing it. And then even if you have tested it or a similar prototype, then you can use FEA to go to the next step for the next sample order or the next iteration of the prototype and make a simulation baselined off of the previous testing. And you will save a lot of time just doing some of these quick checks over FEA instead of making the parts. And the third benefit is optimization. And I think this is really important because a lot of things similar to seal that you don't really see when you test the part one time. You test a part to ultimate failure, you don't exactly know where the stresses are higher, where they're lower. You can see where it fails, how it fails, and make some good assumptions. But with optimization, you can reduce the weight of the part, optimize the seal, change some stiffnesses. You can do a lot of things to really optimize the part. And I think this is one of the main benefits of FEA because when it comes down to a lot of the other things, you're going to have to do real life physical testing to really verify the part. But you're never really verifying that it's optimized. So this is a part, the FEA is a step where you can do a lot of things like that.
Can you provide some tips when performing this type of analysis?
I think it's important to establish a baseline with FEA if it's possible. It's not always possible, but it's very helpful. So whether you use a similar part or a first iteration of the prototype and having some real life testing, then setting up a model and a simulation, modifying the materials, mesh, the setup to match the real life testing. And then you can modify the model and the steps based off that, but keeping the setup similar is very helpful. Then you can compare the improvement and compare the stresses and be more comfortable with it when you have a baseline with a proven test. Another tip I have is, not to just 100% rely on the simulation and just submit the results and that's it. Think if it makes sense. Use intuitive knowledge on physics and hand calculations to compare if it makes sense to you. Why a certain part would fail a certain way or why a stress would be higher here. If it doesn't make sense intuitively, it's probably set up wrong. And finally, I'd say simplify the model or the assembly. You don't always need to do a full assembly, long study on FEA. You can use you can break the part down into components and test those on their own. You can also, do axisymmetric symmetry, which basically takes a 2D slice of the part and considers it symmetric around the axis, and that saves so much time. You can also do 2D models, do a quarter symmetry, half model symmetry. So there's ways to simplify the model, and you can think of what you really care about and break it down to that and focus on doing a FEA study on that part.
What are some useful FEA studies for suspension components?
So there's the ultimate static loading, which is a more basic study to just determine the overall integrity of the part, or the assembly and the required ultimate loading. It can also be used for shape optimization. You can see some areas where the stress is not too high and you might want to reduce the weight of the assembly. You can also use the FEA for buckling of complicated parts. This is really important for steering tie rods especially. The real life does not match the theoretical testing. The theoretical, whether you use FEA or math, and this is especially true for cylindrical shells, so tubes. If you have a bar linkage, or even if you have a plate, the buckling is going to be more similar to the theoretical, but with cylindrical shells, there's a big difference between theoretical and the actual real life testing. So it is important to have some sort of testing or baseline to judge your FEA off of. But with FEA, you can include imperfections in the shape, which will allow you to see closer to what the real life will be. There's also different materials and cross sections from the rod ends to the tube, and the load is usually applied on an offset on the ball stud, so it can be very useful. Contact stress is also a good FEA study when you're looking at the part at a component level. You can review the internal contact stresses between the raceway and the part, whether it be a ball stud or inner ring. You can check the stresses at the working load, the ultimate load, make sure it is sufficient for the material you're using, for the required cycles and allowable wear. So, basically you just figure out what the contact stresses are going to be on the part and determine that it will be useful for the working load and the ultimate loads. And then finally, the seal is very important for us for a couple of reasons. You can check the seal movement at all the working angles. So not really applying the load to the part, just moving the stud or the inner ring and checking what the boot's going to look like. You can verify the part's going to be properly sealed. And you can also check the interference around with other components. You can see where the boot's going to be at this angle and make sure that it's not interfering with anything else, whether it be the knuckle or the steering rack. And finally, you can verify the stresses on the seal at full angle to make sure that the seal is not being overly stressed and the life will be intact for the seal.
And that's all for today. Thanks for joining us for 4 Questions with an Engineer.